One convenience of working with orthonormal bases is the ease of computing the coordinate representations of vectors. This is described precisely by this theorem. Suppose V is an inner product space with orthonormal basis B containing vectors v1, v2 up to vn. Then, every vector v in this inner product space can be expressed as a linear combination of these vectors where the scalars are obtained by taking the inner product of vector v with each basis element. In other words, the coordinate matrix of vector v with respect to basis b is given by this n by 1 matrix whose jth component is the inner product of vector v with vector v sub j. To illustrate, consider R3 with this orthonormal basis. So considering vector 1, 2, negative 1 in R3, the inner product of V with V1 with respect to the standard inner product is 1 over square root of 2 plus 2 over square root of 2 plus 0. That's 3 over square root of 2. The inner product of V with V2, this is still with respect to the dot product, is negative square root of 2 over 6 plus 2 square root of 2 over 6 minus 2 over square root, rather, minus 2 square root of 2 over 3. You can check that it's equal to negative square root of 2 over 2. And finally, the dot product of V with V3 is negative 1. So the theorem tells us that vector 1, 2, negative 1 is equal to this linear combination. And so the coordinate matrix of 1, 2, negative 1 with respect to basis B is given by this 3 by 1 matrix. From now on until the end of this video, we're going to work with Rn with the standard inner product. Recall from the last video that if W is a subspace of Rn, then every vector in Rn, say V, can be expressed uniquely as a sum of two orthogonal vectors, one from W, the other from the orthogonal complement of W. The vector W1 in this equation is called the component of V along W, or the projection of V on the subspace W. And this will be denoted by this symbol. Observe the difference between these two notations. So we previously defined the notion of the projection of a vector on another vector. So in that case, we used the subscript, or we used as subscript the vector. So in this definition, the subscript is the subspace. So here, we refer to the projection of vector V on vector U, but here we refer to the projection of vector V on a subspace, not just on a single vector. So what if W is spanned by two or more vectors? In this case, knowing an orthonormal basis for the subspace will be helpful. In general, if W has orthonormal basis given by vectors u1, u2 up to uk, then the projection of a vector v on the subspace W can be obtained using this formula. You should remember that vector v need not be an element of W. Don't confuse this with the coordinate representation of vector v. It's important to remember that this theorem need not hold if this set is not an orthonormal basis. So to illustrate, consider the subspace W of R3, which is spanned by vectors W1 and W2. W1 is 0, 3, 1. W2 is 2, 0, 0. So let's find the projection of 1, 1, 3 onto W. So first we note that these two vectors are linearly independent. So they form a basis for W, but this is not an orthonormal basis, although they are orthogonal. Okay, the dot product of 0, 3, 1 with 2, 0, 0 is 0. So they are orthogonal, but they are not unit vectors. So we should normalize W1 and W2 first in order to obtain an orthonormal basis for W. The length of 0, 3, 1 is square root of 10. So we just multiply, or we just take the scalar multiple of this vector by 1 over square root of 10 to obtain this. On the other hand, 2, 0, 0 has length 2 with respect to the standard inner product. So the normalization for this vector is 1, 0, 0. So this is now an orthonormal basis for W. So applying the last theorem, the projection of V on W is obtained by taking the linear combination of these orthonormal basis elements with scalars given by the dot product of V with U1 and dot product of V with U2. So you can verify that the projection is equal to the vector with components 1, 9 over 5, 3 over 5. As a consequence, 1, 1, 3 is equal to the projection of V on W plus the component of V along W perp. And what is the component of V along W perp? You just take the difference V minus the projection of V on W. That is 0, negative 4 over 5, 12 over 5. You can check that this vector is in W perp. It is orthogonal to 0, 3, 1 and to 2, 0, 0.